Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show, bringing you a really awesome guest today on a really exciting topic, someone that's involved in creating technologies and a better tomorrow for all of us. Today, we have the honor of being joined by Dr. Elica Kyoseva, who is the director of the Quantum for Bio program at Wellcome Leap, which is a really fascinating $50 million program, $40 million of research funding and $10 million additionally in challenge prizes, focusing on identifying, developing, and demonstrating biology and healthcare applications of quantum computers that are expected to emerge over the next 3 to 5 years. Dr. Kyoseva completed her Ph.D. in quantum optics and information at Sofia University in Bulgaria. She then moved to the Center for Quantum Technologies in Singapore as a postdoc, and 3 years later, she established her own research group in quantum engineering at the Singapore University of Tech and Design, subsequently spent a year at MIT as a research fellow in the Nuclear Science and Engineering Department doing research on quantum control and engineering. In 2016, she was awarded the Marie Curie Fellowship for Research Excellence by the European Commission. Then she relocated to Tel Aviv, Israel, and continued her research in robust control methods for quantum computing at Tel Aviv University. She's also, in between all that, has served as a sort of a quantum venture capitalist. And then in 2020, in September, she took a senior role at Boehringer Ingelheim to develop applications of quantum technologies and quantum algorithms to drug discovery processes, ultimately working at the cutting edge of quantum computing technologies to improve the lives of humans and animals. And then moved on to the Wellcome organization. And Wellcome Leap is a part of the Wellcome Trust that was initially funded to the degree of $300 million to accelerate discovery and innovation in some of these cutting edge areas. A lot of exciting technologies and topics to get into today. But Dr. Elica Kyoseva, thank you so much for taking the time to come on the show and talk to us for a little while.
Thank you so much, Ira, for having me. I really appreciate it. All of the podcasts that I've seen from you are always featuring really interesting people talking about great ideas. And I'm very happy to be here today and also tell you about my work and how I really view quantum computing and what will be the future impact of this technology to human health.
Awesome. I'm really looking forward to this. Let's just start off with you. I mean, I've read a lot about you. I've watched many of your previous presentations. Talk a little bit about the beginning, how you got interested in this space, because I also noticed sort of in your bio at one point, you not just were interested in sort of quantum stuff and the very small, but also were interested in very big things and astronomy at one point. Tell us a little bit about the beginning story.
Yeah, indeed. My interest for science, I would say, started even in math. When I was in high school, I thought I don't like physics, which I think it means that I didn't have a good teacher in physics, but I always liked math. And even yesterday, I was looking at some of my drawings from from my time when I was a small child. Because now my mother is here, so she's showing them to me. And I noticed that all of them, I was joking that it was my Cubism period. So all of the shapes were perfect geometrical shapes, like triangles and squares and circles. So this is the whole picture was very geometrical. So I really liked math indeed.
Mhm.
And then when I was kind of in high school, I still hadn't really found a passion to study very hard. And it wasn't hard for me. So I was excelling at school, but I wasn't so passionate about it. I think the main point is that really I didn't have very good role models at the time. Like for me going to high school, even though I went to one of the best high schools in Sofia, my home city, we were still just studying on the blackboard with chalks. uh, no experiments, no programming, nothing exciting. Everything was just very dry, material. So I didn't have a lot of role models. I didn't have passion for that. But I was doing it because I'm a good kid. I wanted to please my parents and excel. Then ultimately, I kind of got interested in astronomy, and this has always been, I still find it to this day, like even cosmology. I find it really fascinating because at that scale, you realize how small we all are and how small our problems are. And you really kind of get a perspective, I think, that nothing really matters. And, very, very soon, kind of our existence on this earth is just a point in time that is so small, and the universe has existed for so long before us and will continue to exist after us. So it kind of really gives me a perspective to how insignificant our lives and problems are. However, so this kind of led me to rediscover physics, and I ultimately enrolled to study physics at the university, and I specialized in mathematical and theoretical physics, which was much closer to kind of my passion for math and really doing a lot of calculations. And after that, when I was kind of already in my master's level, finishing physics, I joined a group that was working on quantum optics and quantum control. And this is how I kind of went into the field of quantum computing.
And, continuing along that, come 2009, you published your dissertation entitled Design of Quantum Gates and Entangled States for Quantum Information Technologies. And for everyone listening and watching, you can find it online. And it's one of those things that you feel there's probably only 100 people out there that understand this. But the one thing I took away, and I'm going to skewer this a bit probably, in some of our past shows where we've talked about quantum, we've been introduced to the qubit concept in comparison to the classical bit in computers. You introduce a concept in your dissertation of the qunit, which the best I'm able to understand this, it's, in the qubit state, from excited to some base level, there's a bunch of other states. And you classify that as something new, as a qunit, and all the sort of the infinite possibilities that the qubit could become fall within the qunit. And that's all I got out, but I thought it was really cool. Say a couple words about how you focused in on this theme for your dissertation.
Yeah, thank you very much. Qubit is just two-dimensional quantum system, while this is kind of n-dimensional quantum system. So generally people in the community refer to it even as the qubit. At the time we were referring to it as qunit, but it basically just means n states. And the whole idea behind it and why I was interested in that was because we can use less physical particles to represent information. So, kind of because of that, kind of you have more states available with one physical particle rather than when you do have just a qubit. But indeed, so this work was very much in kind of quantum optics and really quantum control. So if you think about the computing stack of quantum computing,
Sure.
You have the level is we have hardware. On top of that, we have the control layer. Then we have maybe some programming level. And then on top of that is the applications layer. So for me, I was really working exactly on the level that was above the hardware. So I was always working on theory, but I was working to solve the problems of the hardware. So can we design better control methods so that our qubits that are so sensitive to the environment would actually, perform better and stay coherent for longer times. So this was in fact kind of the idea behind my work.
Excellent. And you continue to publish after 2009. And again, for everyone listening and watching, Dr. Kyoseva has an extensive publication record in the peer-reviewed literature. The one that, stood out to me from then your time where you transitioned into pharma at Beringer was this paper from 2021, Royal Society of Chemistry, towards the simulation of large-scale protein-ligand interactions on NISQ-era quantum computers. And I want to stop here before we get to sort of broader themes in quantum drug discovery, because I think here I want you to help introduce the audience. You talk about the qubit as sort of this unit of computation. NISQ era quantum computing, which stands for noisy intermediate scale quantum, where we are beginning to put these qubits together, but maybe we're not to the scale where we are going to be, the quantum computer of our dreams in the future. Talk about the NISQ era a bit, because I think the only place that came up on a previous show was with the folks from NTT. I don't know if you had a chance to watch that episode, but they were working on something called a coherent icing machine, which now doesn't make delicious icings for cakes, but does cool things with optoelectronics. Another sort of a NISQ era model. But take us a little into the NISQ era, if you would.
Yeah. So basically, the NISQ era is the year we currently are, and it was a concept that was introduced by John Preskill to kind of really make a differentiation between these large quantum computers that will be needed. Not only we'll be able to, but we really actually need them in order to run the exponential speed up algorithms that have really the big promise of quantum computing. For example, everyone that has any interest in quantum computing knows Shor's algorithm for factoring, and also Grover's algorithm for search. And these are actually algorithms that would require many thousands of qubits and very long run times on a quantum computer. And they will never be able to be executed on the devices that we currently have that still have noisy qubits, so there is no error correction yet. There's error mitigation, which means we use tools to kind of, reduce the errors as much as we can. But our physical qubit is also still our logical qubit. While going forward, the fault tolerant regime would really change in the fact that our logical qubit will be, a collection. It will be kind of executed with the help of maybe 1,000 physical qubits. And this logical qubit, because it will be already completely stable and it will not have any errors. So once we have these machines that are built out of the logical qubits, they will be able to run for a long time, for days and weeks, and execute the big scale computers. Mm-hmm. So on one hand, this is actually a very interesting idea. What do you focus on? Do you focus on fault tolerance algorithms? Do you focus on NISQ algorithms? And the paper that you cited was indeed the first one that came out from my work, and the rest, of course, of the team, together with our partners from QCware, on NISQ algorithms, and actually kind of doing the first step towards calculating interaction energies on quantum computers. And we decided to focus on NISQ because the current way that interaction energies are calculated on even classical computers, we felt that they will not work in the quantum computing case. So we really wanted to explore that area and see what we get out of it. And in fact, the paper looks at this kind of energy partitioning approach called SAPT. Okay. Which stands for Symmetry Adapted Perturbation Theory. And we show that if we use ground states of the two molecules in question, the ligand and the protein. So we show that if we use ground states from quantum computer using this symmetry adapted perturbation theory, we can calculate the interaction energies more accurately than by using it on classical computers. But in fact, this is actually a very big problem. I personally have, I do believe that we need to develop algorithms for small scale fault tolerant machines. And this is why I actually structured the program that I currently lead, Quantum for Bio, at Wellcome Leap. So our goal there is really kind of algorithm development, but from going from these algorithms that I mentioned, like Shor's and Grover's and other that are known to be really expensive in terms of computational cost, can we actually design some algorithms that will be much cheaper in quantum computational cost so that we can run them on small scale fault-tolerant computers?
Mm-hmm. And before, I'm going to go one other place before we get to the Quantum for Bio program at Wellcome Leap, and that is your recent paper from just a couple months ago, drug design on quantum computers, where Beringer and BASF and Google and a bunch of other folks got together. And I think, again, for everyone that wants to check out Dr. Kyoseva's other presentations, she gives a really great presentation entitled Quantum Computing Use Cases for the Pharma Industry. You can find that on YouTube. And here you do a deep dive. You sort of look at the landscape in terms of, once we do this magic, which you're working on now and the team, we're going to think about drug discovery. We're going to think about genome sequencing in a different way. And you talk about, okay, here we have these molecules and the ligands. They have electronic fields. They have spins and forces and waves and all sorts of other things happening at the physical level. Take us through a little bit of what you talked about in that presentation, because I think it's important to sort of see how you view sort of the evolution of the use of these tools, first in terms of some of these complex chemistries and physical forces, maybe a little later on, more digital twinning, the modeling of the wetter world of biology and cell systems. Yeah. Take us through that transition. I think this is a very important point here to sort of understand how you view the landscape looking out.
I think it's very important that when we want to use quantum computers, or let's say quantum algorithms, it's very important to really choose the problems accurately. So we always need to choose a problem that is very hard to solve, exponentially hard to solve on a classical computer. And when we look at chemical systems, molecules, let's say small molecule drug design, this is the perfect test bed to actually develop algorithms, because these systems, just to describe them on a classical computer, require resources that scale exponentially. So if let's say we have some small molecule and we can create its perfect representation on a classical computer, and we want to increase this molecule with one electron, we just want to add one more electron to it, we need to double the resources that we used for the first molecule in terms of classical resources. So every time we add one more particle to our system, we need to double the resources available. So in terms of molecules, this runs out the current computation possible on even the biggest supercomputers very quickly. But this is actually very small. So the usual size of even a small molecule drug is around 200 to 300 electrons, was the size of the most sold drug of Boehringer Ingelheim. So the question is, how can we predict the properties of these molecules if we cannot calculate them? And this is why drug discovery is such a long process and also such an expensive process, is because humanity basically cannot calculate their properties accurately because we run out of computational power very, very quickly. So what people do is, of course, you use a lot of approximations that smear out the quantum effects. You do a lot of experiments, a lot of time in development, a lot of, people are, of course, always using a lot of computational tools, but ultimately everything is always an approximation of the actual behavior and properties of the molecule in question. So this is the perfect really example for a system where quantum computing can help, because quantum computing, to represent the same information, doesn't require doubling of the computational space. It requires just adding one more qubit. And this is where kind of the fascination comes. And we are really working hard to design algorithms that will be able to really kind of map efficiently the state of a chemical system, and that we can calculate its properties with the help of a quantum computer.
Outstanding. Outstanding. So yeah, let's segue to Wellcome Leap now, because again, a fascinating organization. The mission statement on the website: building bold, unconventional programs, funding them at scale. Again, looking 5-10 years out at what might seem impossible today, but it's also Wellcome Leap divides itself with global ARPA for health. You have a former DARPA director leading everything in Dr. Regina Dugan. Very exciting, and we profiled DARPA guests on the show before. Wonderful model for really innovation without worrying about do I have a product to commercialize next year. Take us into Wellcome Leap as an organization. Obviously, you arrived on the scene. You are a program manager that is leading this specific portfolio of Quantum for Bio. Walk us through sort of what that's all about, because it sounds so exciting, especially from what you've been doing, and now you have sort of a real sort of like playground to play in for a while.
Yeah.
and experiment with these ideas.
I fully agree, and this is why I took on this challenge, from Wellcome Leap to start the program and also to lead it down the line, because even though also what I said before was we do know that quantum computers will be able to help solving some of these problems, actually figuring out the details turns out to be much harder. So when we look at the details and how long will it take to load information on a quantum computer, how many measurements you need to do after that, it seems like even for some of these problems where we will require photon quantum computers, it might be still hard to run the calculations on a quantum computer. And from Björn Geringelheim also we had this work on molecular dynamics, where we looked at can we do the way we do classical molecular dynamics on a quantum computer, and unfortunately it turns out that it's going to be way too costly even with a quantum computer. So there is still a very big knowledge gap into what is the useful thing that we can actually achieve and do for human health with the help of small quantum computers. And this is how I decided to join Wellcome Leap, because from my work at BI, I got very passionate about that field. It was kind of my first time more or less transitioning from academia and always working on research, but kind of now working in a particular industry, and this was the industry of health. So I was very happy that Wellcome Leap is, this kind of organization that is really focused on human health. As you mentioned, we are funded to a big extent from the Wellcome Trust, but we are an independent, registered in the US nonprofit organization that funds programs. And we are honestly also a very small organization that is punching really above its weight. I think just recently we had the announcement that we already have over 1 million researchers globally that are part of our network. And my program is still kind of, developing. I actually still have not, it has still not started. I'm now in the selection period. And the way we do it is basically we have 3-year programs that are led by a program director. And they're usually $50 to $60 million. And the whole goal is really in these programs is to really bring scientists and teams around the world to work together towards the common goal that they wouldn't be able to achieve independently. So all of the other programs, except for mine, which is actually a challenge, but I can tell you more about it. But usually the programs are very ambitious programs that are decided mostly by the program director, and a very ambitious goal. And then you have the funding at hand, which is, as I mentioned, about $50 or $60 million to spend them towards reaching this goal in the next 3 years. In my case, because of the lack of really quantum computing resources, we decided to structure the program differently. And what it is, it's more like a challenge. But we will have a competition, it's only at the end. So before that, I will be really supporting teams that hold the promise to really show something useful that can be executed in quantum computers that are expected to exist, 3 to 5 years from now, or 3 to 7 years from now. And I left the application area, so the human health application area, wide open. I had a bit of a kind of inspiration for that challenge from a previous DARPA challenge that really kickstarted the autonomous vehicles industry.
Okay.
And I think challenge was, I think, in 2009 or 2011, over 10 years ago. And what they did was they said, come with your autonomous vehicles designs, and there is this trace in the desert, and whoever manages to finish the path in the desert, then they would win a challenge. So in my case, the desert is really the quantum computing resources. And what I really wanted to bring and to focus is really people kind of to aim to that particular area that is the target in my program, which I believe will be able to be run on quantum computers in the next 3 to 5, 7 years. But that it also has to be useful. So it really has to be something in human health. And just another thing to add is I really noticed how important it is when I was at BI to have quantum algorithms researchers work really daily with people that are concerned with human health problems, and this is their kind of life and their work. So I really wanted to bring in my program these two types of expertise to interface, and because I think this is how we will get to innovation. So that's why I want every team in my program to be really comprised of people that know quantum algorithms and can, develop new ones, but also to have very strong human health expertise. So people that have not worked on quantum computers, but for example, let's say if it's protein folding application, they're actually on top of protein folding research. They know what is the best in the world at the moment method, and they would be able to kind of work together to push forward the quantum algorithms for that application.
What's it been like? I mean, because I mentioned briefly in your bio that you also along the way had spent time consulting as part of a sort of quantum venture capital group, and I know in my own experience with VCs, there's a bunch of people there that used to be in pharma and understand pharma and drug development and help coach sort of the portfolio companies and all that. With quantum computing and the stuff you're involved in, it's almost like it's happening in real time. Like you not just have to evaluate sort of the groups you're going to be working with, but you got to stay up to date on all this stuff because it's happening. The future's happening as we're talking right now. What's that been like in terms of your preparation and evaluating some of this stuff?
Yeah. So the truth is that I did spend, the VC that I was part of wasn't really focused only on quantum computing, but what they were actually doing at the time was they were kind of interested to explore the field and to start making investments in it. But as someone that is not very familiar with the field, it's very difficult to judge which startup has actually something valuable at hand, and which one is just kind of representing something that they wish to be true, but maybe it's not really based in reality and in science as well. So what I did for the VC was actually I was an entrepreneur in residence and also scientific advisor. I was working on my own idea actually in quantum computing, and I wanted to have my own startup in the field. And at the same time, I was looking at the quantum computing companies that were coming to raise money from them and advising them, maybe doing some due diligence as well, and kind of sharing with them my honest opinion on the technology, on the teams, etc. Ultimately, what happened was this really was taking place when Corona was also picking up. So I think I joined the VC, maybe it was January or February 2020. So very quickly after that, the whole world really changed. And for me personally, to find a co-founder, because this was my goal joining the VC, I wanted to kind of find a co-founder. I didn't manage to find someone that was suitable, someone that was based in Israel, where I was living at the time. So ultimately, after about like nine months, I left and I joined Boehringer Ingelheim, which was hiring globally, so it didn't matter where you're based. But for me, it was great to see, because I would say 2020 was probably the start of the peak when quantum startups were kind of rising. We had maybe only a few from maybe 1 or 2 years before that. Of course, the bigger ones were already existing, but this was really the beginning of the peak of quantum computing startups. And now, I don't know, 4 years later, 3 years later, we have so many quantum computer startups, and they're really like growing like mushrooms all over the world, in every country, especially obviously in Europe and Asia, and in the US. So for me, it was really cool to be part of a venture capital fund and to see how they think, about their investments and what they would invest in.
One topic that, well, it's obviously been hot everywhere, but it's, we've done quite a few episodes on artificial intelligence as of late, and applications of AI, machine learning in some of these areas, whether it be, drug discovery or protein folding, or some of these themes that you're going to be looking at. What's sort of the connection between your world of quantum computing and artificial intelligence, and sort of what do you foresee as sort of the evolution of all of that? Because I obviously, again, at the end of the day, with that magical quantum computer that you're going to build sitting there, we push a button and we solve all drug development issues in a couple of seconds. What are some of these other tools that you envision sort of partnering with quantum computing along the way as you build out this future, whether it's AI or digital twinning or whatever the other stuff may be that gets you excited in terms of tech?
Yeah. The truth is that I feel quantum computers, at least for the near future, are best suited for this kind of small data, very hard problems. And I think because of that, they will not have a very big intersection in the near future with, for example, AI, because to have access to a large amount of data that you are able to crunch, more efficiently with quantum computers, you need to be able to first load these data on a quantum computer. And this is in fact very difficult when it is about, some big data and also classical data. So not data that is coming maybe from a chemical system, but really, kind of images or information about portfolio prices, etc. So I think that there is still some time until it is really clear where will be the perfect intersection and the most useful problems that quantum computers will kind of help together with AI.
Got it. I appreciate that. One thing that I neglected to mention when I was reading through your bio was the fact that you are also, in addition to sort of pioneering the future of quantum computing, you are extremely passionate both about gender inequalities in STEM fields and exciting sort of the next generation in these areas. In addition to quantum computing, you served as an ambassador for STEM to the United Nations Women's Committee in Singapore, managing director in Israel of the global nonprofit Girls in Tech, on the advisory board of She Quantum. Talk us through a little bit about what you're doing in terms of encouraging the next generation, encouraging girls to get involved in STEM and quantum computing. This is another very exciting and interesting part of your bio, and I want you to talk about it.
Yeah, thank you very much. Indeed, there is so much still gender inequality in especially technical roles in quantum computing. Even in my own, future and current program, Quantum for Bio, when I looked at the abstracts that came in, the women, PI or even co-PIs were probably less than 20%, maybe around 10 to 15% of the abstracts actually did have women PIs and co-PIs. And this is something that I have also faced and I have struggled with in pretty much every role that I've had so far. The room is always filled only with men. And there is very rarely another woman. And again, now we have a lot of quantum startups, so there are many women working in these startups. But when you look at the technical roles, I would say that we are still about 20% of these roles are actually occupied by women, and this really kind of makes you, first of all, everyone kind of, when you're surrounded with really smart people, and most of the people in quantum computing are actually, they're pretty smart. So it's very easy to feel, the imposter syndrome.
Yeah.
I still to this day feel like that, and I think I will never completely get out of a feeling like that. And I think I personally also never really had a mentor that did something for me that made me kind of believe in myself. And I would say that this is probably only until now, because my current manager, Regina Dugan, she's been really great and she's been really supportive of me. But until now, it has always been a struggle, and you are kind of feeling like you're swimming against the current. And I really want to help, especially, like kind of the younger generation of girls, whoever has interest. I definitely don't think everyone should go into STEM or, science. But if someone has an interest, I don't want them to feel the way I felt, that, they're not as smart as the boys in the room, or that they would have to sacrifice having a life outside of work, and would have to sacrifice, having a family, for example. So whenever there is a possibility about that, I always try to get engaged. And for example, in Singapore, when I was partnering with the UN Committee Singapore, I was hosting high school girls that had a lot of interest in quantum computing. I was trying, to show them a day in the life of a scientist. They were visiting my lab, and I was coming up with some cool ideas for them. I'm always very happy also to speak to kind of, to be a mentor for younger women that are maybe now finishing their PhD or are a little bit after PhD and are facing, challenges in their careers. I would be really, really happy if in 10 to 20 years, the gender inequality in our field has really subsided. And I do think it's really possible if there is really a concentrated effort. And why I say that is really from my experience at MIT. So you did mention I was at MIT for a year, and I was, except for kind of research, actually at the time I was also involved in teaching, but also really understanding the culture of MIT, because the University in Singapore, that I was a faculty member at the time, was in partnership with MIT. So we wanted really to bring also a big part of the culture as much as possible. So what is special about MIT is that really until the 70s, they also had absolutely brutal gender inequality problem. Then they decided to really end that. And they really started to, admissions to really target women, to have more diverse population, student population. And currently MIT, at least at the time when I was there in 2013, they had a 50% or even a little bit more than 50% undergraduate students, women. So it really helped me. Also, my university in Singapore that I was at the time, because we were also actively recruiting, gender diverse student population. We were also, even though we were an engineering school, we had a very good gender balance. So this really helped me understand that it is possible to change a field or a university, as long as you make an effort in it. Unfortunately, I think quantum computing is still not there. There are maybe just a few people here and there, everyone trying to maybe dedicate some of their time to that, but there is still a very long way to go.
Got it. I appreciate you sharing that. I noticed that in addition to managing this really bleeding edge portfolio that you have per Wellcome Leap, you also do get out on the sort of the public circuit. I saw that you were, I think, at the American Physical Society meeting a couple months ago. There's something called Quantum Tech 2023 that's coming up later in the year. Anything else sort of on the calendar in terms of public facing initiatives that talks you're going to be giving, conferences you're going to be presenting at, places we can listen to you or meet you possibly? Anything else for 2023? Please take the floor.
Yeah, thanks, Ira. So actually, the APS meeting, it was I wasn't there. It was my team at BI, but of course they included me as an author in the presentation that they were giving.
Nice.
And indeed, I was at Quantum Tech 23 in Boston. That was, I believe, in April, end of April, about a month ago. For the rest of the year, I'm really now in a time when I'm kind of very deep in the selection of the performers, the way we call the people that take part in our programs to solve our problems. So I'm kind of really keeping low profile. So probably I will be in London around the end of September for Quantum Tech.
Awesome. No, it's really awesome stuff. I'm so excited for you and the fact that you have the ability to build this completely from scratch, and really rooting you on, and will continue to follow you as you proceed over the coming years with this really cutting edge work. Again, for everybody that is going to be listening to this particular episode of our show across the various podcast networks or watching on our YouTube channel, again, you've been listening to Dr. Elica Kyoseva, Quantum for Bio Program Director, Wellcome Leap, doing really amazing things to build this bold and fund this bold unconventional program in quantum computing to make major impact in human health. Elica, I want to thank you for taking the time out of your very busy schedule to come talk to us, educate us on these very complex themes, which you make very easy for us to understand. Obviously, thank you for everything you're doing. And as we like to say here on our show, thanks for helping to create a better tomorrow via what you do. Really, really great story. And I'm looking forward to following you further.
Thank you very much, Ira. It was really, really a pleasure. And I'm very much looking forward also to following your podcast.
Good seeing you.